Welcome to this NPTEL lecture on principles and techniques of modern radar system. Now, we were discussing MTI filter, in that we have also seen staggered PRF MTI radar. So, what I will now take an example and see that what we have discussed, based on that how we can calculate the first blind speed, what is the effect of pushing the first blind speed further away by staggering the PRF. So, let us consider a problem that a S band radar let us say at 3 gigahertz utilizes staggered waveform with 4 different PRFs. 4 different PRFs. Let us say the PRFs are 1, 2, 2, 2 hertz, then 1031 hertz, then 1138 hertz and 1 kilohertz. So, let us calculate. The first part is calculate the first blind speed of this radar. So, this staggered radar, what will be the first blind speed? So, here we want to find out that what is the common or what is the common multiplier of these. So, actually that is a there are various theories for finding these numbers, but here let us say that we can take it as the, for this one I can take N. So, we are calling it N1, 27, N2 let us say 32, then N3 is 39 and N4 is 33. If you see that, if you multiply 33 with this, you will, and 27 with this, you will get the same thing. So, this has been obtained, and you see that there are no these numbers are given. So, we can say that first blind speed that will occur at anyone, let us say that, let us say the last one, because there is 1000 here. So, first blind speed occur at the Doppler, which is N4 FR4. So, that will be 33 into 1000. So, 33 kilohertz is that Doppler. So, what is the V blind fast for staggered? We know this formula is simple, that lambda by 2 into this. So, we can make this is 3 gigahertz. So, lambda will be 0.1 in meters by 2 into this 33 kilohertz. So, this blind speed will come in meter per second. So, if you do this, this will be 1.65 kilometer per second, or if you convert it to kilometer per hour, it will be 5940 kilometer per hour. So, you see, as I said that typically the aircraft's fly is 1000 etc. kilometer per hour. So, if the first blind speeds come like here, it is good, but let us compare that had we not done this staggering and suppose we have operated with a constant PRF. Now, which is the how to get the constant PRF, that let us take some average. So, if the that is taken as the PRI average, then we know that in that case our FR average, that formula we have given. So, that will be 4 by 1 by this 1222 plus 1 by 1031 plus 1 by 1138 plus 1 by 1000 in hertz. So, that will be 1090.8 hertz. So, what will be the blind speed due to that? Blind first average. So, that if you calculate that again those things, so it will come to 54.54 meter per second. So, here it was kilometer, but in kilometer per hour if we convert that, it is 196.34 kilometer per hour. So, you see, compared to a 200 kilometer per hour, by staggering we are pushing it almost 30 times, I can say. So, you see thus there is tremendous improvement in this. But what is the price we are paying? Definitely in nature we cannot get anything free. So, the price we are paying in the unambiguous range. So, for this average thing, what will be the unambiguous range? So, unambiguous range for this constant PRF radar. So, that will be C by this 2 FR AV, C by 2 into. So, if you do that, that will give you 137.51 kilometer. Whereas, what is the scarce for the staggered PRF radar? So, R unambiguous, the staggered PRF, in that case C by 2 FR staggered. So, FR staggered we have already found out, it is 33 kilohertz. So, we can put that C and those things, that will give you 4.55 kilometer. So, you see that drastically this is getting reduced. So, if you are more interested in the velocity, you go for this. So, we have seen the effect of staggering. Now, I will come back to the point where we have left last time, that you see the 4 PRF staggering is a common thing, but we do not know how to make the transfer function of the MTI filter if there are 4 staggering, because we have solved the problem for 2 staggering frequencies. So, also there is another point, that how to choose the stagger ratio. That means, the point I was saying, that how to choose that N1 is to N2 is to N3 is to N4. So, there are various algorithms, those are mathematical things, I am not going into that details, but generally this stagger ratio is chosen closer to unity, and that gives you good results. Now, to come back, that how to find the HF for a multiple staggered MTI filter. So, the 2 one we have seen that we can always do with 2. So, to determine in this case the algorithm for more than 2 staggering PRFs, first I will say that assume several MTI filters, one for each combination of 2 staggered PRFs. So, you determine now for 2 you know how to do. So, you can find out the individual PRFs for them, then you overall response, overall HF is nothing but average of individual HF, or I will say HIF. So, what does that mean? Suppose I have that case of 4. So, if I have the 4 staggering PRFs, let they be FR1, FR2, FR3 and FR4, 4 staggering PRFs. The corresponding PRIs will be T1, T2, T3 and T4. So, what we will do, first we will find the filter response with, let us say, first find filter response with T1 and T2, that we have already seen, and let us call that filter response. So, find filter response by staggering FR1, FR2, that means. So, let us call it T1. Then you do it with T2 and T3. Let us call that filter response H2. Then T3 and T4, that is H3, let us call. And finally, that T4 and T1, that we will be calling H4. Now, by that overall HF, what will be the overall HF? Overall HF is 1 by 4 into H1F plus H2F plus H3F plus H4F. Okay. So, we can draw the gain, that HF square for this overall response versus the relative velocity VR. So, the graph will be, there will be some initial kinks, but otherwise that will be a flat response up to the first blind speed. So, clutter is removed, you see first blind speed pushed away and more or less uniform response over MTI passband. So, this is a good way. Now, we will see that how to characterize this filters, that each MTI filter we require some performance matrix to measure that how much it could remove clutter. So, there are 3 performance metrics. So, I will say that performance metric of MTI filter. There are 3 such. One is called Clutter attenuation, or its symbol is CA. The second one is called moving or MTI. MTI improvement factor and the third one is called sub-clutter visibility. So, we will discuss each one of them. So, MTI improvement factor, this one is called sub-clutter visibility, and MTI improvement factor is generally given the symbol I. Okay. So, we will now discuss one by one. So, first is the clutter attenuation. See. So, consider that I have the MTI filter. So, the input to this is the signal as well as corrupted with clutter. So, if the clutter power, input clutter power, clutter is a random process, but we know that we can through the PSD power spectral density we can find its power. So, let us say that that is input is Ci and output clutter power is Co. In that case, the Ca clutter attenuation will be the ratio of these. So, I can say that MTI filter input clutter power divided by MTI filter output clutter power. That means, basically it is a ratio of Ci by Co. Okay. Now, if we can model the clutter power, then or clutter we can model. So, if we can model the power spectral density, then we can find out the power. Let us do that. So, let us assume that the clutter is modeled as a Gaussian distributed power. You know that generally we take Gaussian because it is mathematically tractable. Also, there is a central limit theorem which says that if there are no dominant scatterers and there are many dominant scatterers of this clutter and no one is dominating, but there are many, usually 4 5 is there, that is sufficient, then whatever may be the individual clutter power spectrum, the overall will be Gaussian. So, with that knowledge we can say that if we model the clutter power spectrum, now also I recall that we have seen that actually clutter's power spectrum is something like this. If this is your f, then frequency. So, there will be center at 0, it has a spread of delta f, sigma f, and that we have seen at the beginning. Also, we know that due to the pulse radar, that spectrum will get repeated at every integral multiple of FR. Now, first this is the PSD. So, let us analytically express it, that if clutter's power spectrum is SF and obviously it is centered at 0. So, we can write it as PC by Gaussian PDF. So, 2 pi sigma f e to the power minus f square by 2 sigma f square. Here we have assumed that it is a 0 mean, that is why mean is not coming here. And what is PC? PC is the, I should I should write what is PC? PC is the constant clutter mean power or clutter mean power, that is PC. So, now I can calculate from that what is the input power. So, input power will be from minus infinity to infinity. I will have to have that SF dF. This is power spectral density SF. So, overall frequency if I integrate, I will get a. So, this is nothing but the integration of that PC by root over 2 pi sigma f e to the power minus f square by 2 sigma f square df. Now, you know that if I take out PC out, then what is this? 1 by root over 2 pi sigma f e to the power minus f square by 2 sigma f square df, and this is nothing but area under the whole Gaussian curve minus infinity to infinity. We know that value is 1. So, the answer will be PC. Okay. Now, next we will have to determine the output power. So, I have the MTI filter. Now, I am know the input I am giving, that I am giving that SF. So, what will be the output, that I can write from the filter theory. Remember, this SF is powered spectral density, and output I will get CO. So, CO is minus infinity to infinity HF square SF dF. So, this integration we need to do. Now, HF we will have to now take some value. So, if you have the single DLC, suppose single DLC MTI filter, if I have that, then I know that what will be HF. HF square we have already derived, 4 sine square pi f by fr. So, we will put that. So, C naught will be minus infinity to infinity P c by root over 2 pi sigma f, then e to the power minus f square by 2 sigma f square into this 4 sine square pi f by fr df. Now, as we have seen that if you look at the spectrum, that this spread is very small. So, I can utilize that, and we can say that this power spectrum, the clutter spectrum, that is significant only at small f. So, I can assume that f by f r, that is much less than 1, because only over a very small spread the power spectrum is significant, but f r is quite larger than sigma f. So, f by f r is very small. If I do that, then you know this sine square term can be approximated by the square of the argument, sine argument. So, I can with that I can write this, that minus infinity to infinity P c by root over 2 pi sigma f e to the power minus f square by 2 sigma f square into 4 into pi f by f r whole square d f. Okay. So, I think you have recognized what is this, because I can take all these things out. I am deliberately taking out those things which I do not need. 4 P c will go out, pi square will go out, and here I will take that f r square, it is also a constant with respect to f. So, I am left with minus infinity to infinity 1 by root over 2 pi sigma f, then e to the power minus f square by 2 sigma f square, and actually I should say that f square into d f. So, can you see what is this? Can I say that this part is nothing but the second moment of the Gaussian PDF? So, I can easily write that it was CO will be the 4 P c pi square by f r square into sigma f square, because second moment is the sigma f square for a 0 mean case. So, this. So, now I can find out what is Clutter attenuation. Clutter attenuation is C I by C naught, and I have seen that both the things I have evaluated. So, if I put that, it will be f r by 2 pi sigma f whole square, and remember that this is valid provided I have sigma f is much less than f r. Usually it is true that f r, the PRF that is there, that is much larger than sigma f, but if you have that in a very the platform motion and other things, sometimes may make that sigma f is not, this is valid, then you will have to go to the basic equation and try to find out, evaluate that integral, but otherwise this is a good one. So, you see that for a single DLC, this is the thing for clutter attenuation. So, it is proportional to the f r square, the PRF square, and since sigma f is very small. So, you have a good number. So, lot of clutter gets attenuated. Okay. But as the in noise, that we are more interested in, because this is a detection problem. So, we are more interested here also, like communication, that what is the, how much clutter is suppressed with respect to the received echo signal power level. That means signal to noise ratio sort of thing. So, that we call signal to clutter ratio. So, that is more important, because clutter may be reduced, but if the signal to clutter ratio is not improved due to the MTI filter, then there is no point. So, that is the second metric will come, the MTI improvement factor, that takes care of that. Something like your noise figure in case of noise. So, the corresponding thing in this MTI filter domain is called MTI improvement factor. We will take up that in the next class. Thank you.